Hey guys, Eric in the alley. Actually, I'm in the back alley basement today. If you see anything's coming from like the basement, that's going to be this electrical bench. That's all that is. This is where we're going to build a lot of sensors, things to save money instead of having to buy, a name brand if you can make something that works yourself. The pulse sensor I built down here, but what's cool, what I'm doing down here today, that we're not starting a new project. I'm going to just show you how it worked out. Being able to save a waveform. I'm just sitting down here now looking at the waveforms I captured. That was like 2 in 1 day. Pastor Ed's car, I just got done putting a timing belt on it. So I wanted to save that as a known good. The car wasn't even, driven yet. It had a couple warm-up cycles, but it never left the garage. That's going to be as dead on as you're going to get. If you have a car with any kind of mileage on it, it's going to be a little bit different. But sometimes you want to take one right away because you have to get creative. I mean, you're going to use this to check a car, say 30, 40,000 miles. Yeah, the belt's going to stretch a little bit. I know a lot of you people say that should have did it in 1,000 or 2 miles. I still have that opportunity, but sometimes you want it dead on, not even driven yet, warmed up, just to check that you're putting a belt on. If you ever had to put a belt on another one of these engines, you have not driven, not left the bay. So you have a known good just to double check your marks. I check the marks very thoroughly, take an image of it. But one of the things that discouraged me about a 2-channel scope was I wanted to use this for cam and crank correlations because I enjoy doing timing work. So the 2-channel scopes, I was starting to think, I need a 4, then I need an 8. And you see all the different scopes out there. But it's quite easy to get a 4-channel cam and crank correlation with a 2-channel scope. And if you use Hscope software, you could save these images. Like now, that was a couple days ago. I'm going to show you now. And in case you never compared them with, where do you get a known good to compare it with? And how do you do it? Being that it's not going to be taken with your scope and you're not going to be able to import it. So first things first, I'm going to just show you how I got these waveforms, and then we're going to come back and take a look at them now and see what they mean and what you'd do if you got these images and you wanted to compare to see if your car was in time or not. All right, guys, I'll be back, and I'm going to show you how important it is. This isn't one of the cars here. I got in 1 day, and this is the importance of checking known good. The Honda Odyssey, I didn't know where to check. I had to look up the schematics. The Toyota RAV4, from checking known goods and using it to repair, I knew right where to check. In 15 minutes, I had 4 channels out of a 2-channel scope. So that was all in the same day. Now it's a couple days later. I get to just pull it back up, take a look at it. I can manipulate the waveforms. I can do whatever I want with them. The ones I like from Mixed Sig Vado, some of the other scopes, I can't save it. I could just save an image of it. I can't open it up. I can't, put cursors on it again. I mean, and that's an important thing. Or apply a math channel, anything like that. So Hscope, even though it's only going at it with 2 channels, I still felt better using the HS512 than even using Hscope to control the Hantac 1008C. I mean, the 512 gets much better images. So I'd rather have a couple 2-channel images, just keeping the crankshaft signal constant throughout all the images. You could literally take as many as you want and just keep the crankshaft as a constant. 1 channel will always be your crankshaft. Then you switch intake cam, exhaust cam, and ignition. You got 4 different waveforms, but you got 4 channels on that 1 crankshaft signal. So that's great. The pulse sensor, it worked great. I'm very happy with it. It actually, for the HS512, it ended up right in the middle of the sweet spot of its voltage range. The Rotke that I compared it to, I love that sensor. It's a very cheap sensor, so you're not trying to make a sensor that's going to save you a ton with these pulse sensors. It's just doing it for the sake of you build it, and it was just blind luck. I left it tunable, but, the first run, I kind of like it where it's at. So, but the Rotke, I use the 512. If you use the 502, or a scope with a lower input range. The Rocky was getting, I mean, it was producing some voltage. It was 15, 16 volts I was putting out. So that's a lot for a pulse sensor. I think it's because of a smaller diaphragm, but I'm not positive on that. But okay, guys, I'm going to just show you how I got the signals, show you how the pulse sensor worked, and then I'll show you how I put it together and what we're going to do with the next one, how you could customize your own. A couple new sensors we're going to be putting out. All right, I'm going to get right to that part, guys. Okay, guys, these are the scopes I have available. This is the HS512. This is a AES Wave Hscope. I already used this. This thing is invaluable. I know they make a lot of portable scopes that you could carry under the hood with you, but this one I like taking under the hood because it's small. I could lay it on the intake while I'm looking for individual signals. Then I leave the lead there to plug into a 2, 4, 8 channel scope, whatever you want to do. But while I'm under the hood, I don't want to take my tablet. I don't want to take my laptop, and I don't want to carry this under the hood. This just lays anywhere, you know, lays on the radiator cover, anything in the front, so you don't have to keep turning around looking at your screen. You get the signals, then, you know, you line them up. But now, what I'm after, this car has one cam sensor, so we want a cam and crank. The 8-scope is perfect for that. You could get a cam and crank with it. But now we want to add an ignition too, so we have ignition timing. So that's 3 channels, and we only have 2 with Hscope. So if we go to the Mixig Vado, the Handtech 1008C, or this old Modus, to get more channels, it has 4 channels also. It's still going to inconvenience me more, and there's different reasons why each scope is, even though it has the channels available, I'd still rather get a 3 or a 4 cam and crank correlation, say with 2 cam sensors, a crankshaft sensor, and an ignition. I'd still rather do it with this. A lot of people are passing this over. When they look at it, you know, they consider it and they're just saying the 2 channels is a drawback. There's a time and there's a place for more than 2. Getting a cam and crank correlation doesn't have to be one of them. The times when you want 4 channels, like the Modus and the Vado, is when you have a broken car in your bay and you're adding things. You're on the ignition. You're on an intake pulse. You want to add an exhaust pulse. You don't know where you're going yet. But whenever it comes to just taking a cam and crank correlation, the software of this outpaces any of them. And what is very nice about it is the way you could save the file, the ability you have to manipulate it after you capture it and compare it to a known good that you might be getting from rotkey.com. You might be getting it from a forum. You might be getting it from factory service that wasn't done on the same scope. And it's very easy to manipulate Hscope on your tablet. So that's just why I wouldn't get any of these scopes out. I'd just use these 2. And now I know that 101, there's a couple companies that have 2-channel handheld scopes. That would be the same thing as this. Something you could get under the hood and you could be facing the direction that you're back probing, because you have to look at the screen to see if you got a signal. You don't just put the back probe in and leave assuming you're going to get a signal. You want to actually see the scope as you're back probing to know when you're on it, when you're not. So that's just a little tip on that, but we're going to flip around. We're going to go all with Hscope just like I normally would for this. All right, guys, I got the wires out of the loom right there. It's very easy. You take this off the firewall or off the sidewall and then just pull them out of the loom. It was easier back probing them. I got wire piercers in them on the cam and crank signal. Yes, I am going to liquid tape them when I'm done. But this is what I was talking about when I'm under the hood. I like having the 1 channel of the Hscope that just is set anywhere. And then I use a short lead to find my signal. Then whenever I'm done with it, I'll just leave the probe in it, move on, find the next signal, leave the probe in it, and then come back with the longer probe so I could do it all from my cart. Sorry about the exhaust fan. I'm going to fire it up and see if we get a signal on the cam and crank. All right, there we go. That's what, there's only one cam sensor, so the only thing we can time the crank to is that one signal. So this is what I'm going to want to save the image of. You could vary the RPM, do whatever you want, but usually for the cam and crank, I like checking them at idle. That's going to show your slop. You know, it's just a good way to take it. Just go to automotive module. Keep it at 150 sampling rate, 8-volt scale. Just let it record a little bit. You don't need much because it's with the good tight belt on it, there's no movement. I'll give it a little bit of acceleration and that's it. Alright, let's stop that and I'll save it. That's more than enough information for the cam crank. This is our crankshaft signal. This is our camshaft signal. That's what you'd be syncing it with. On Hscope, that's what makes it real easy. You could drag these, you can move them. And once I save this file, this is what would be lining up. Anywhere where these would line up, you'd look or save as a known good. But with a straight up cursor, you'd be looking at the edge. Where it is on this, I don't know, but this is where you'd be looking for the teeth. This is what I'm saving as a known good. I don't have one to reference it to. Okay guys, this is what we'd be looking at. We have no good or no known good cam and crank correlation. We're making our own right now. But if you have the pattern in your software, you could just drag it on top of the crank signal like that. There's always going to be one spot that these lines are dead on, especially on the known good. That one wasn't dead on. This one isn't. But this one, you see how that edge, both of them line up. Now, no matter where you are, you're going to want to count the teeth on the crankshaft, and you're going to want to mark the trailing or the falling edge of your camshaft signal, and that's going to tell you where your timing is. You can measure the degrees on the crankshaft where you are, but whenever you get a known good, you usually don't have the ability to load it in your scope and get the degrees. It's real hard to do with paint. The screen moves a little bit because it's Android, but I just deal with that. You know, it's the tablet, it's not the scope software. It's just always roaming a little bit on me. But that's what you're going to want to save as a known good. You'll be able to check if any Honda Odyssey with a 3.5 is in time just by looking at this mechanical timing. Alright guys, I'm going to just move the probe because we have a good cam and crank now. I'm going to go for a crankshaft and a primary ignition. The secondary, these are little hard coils to get, and it's aimed, the back bank is bank 1. I could easily get number 4, but you know, number 1's the one you want if you're going to do ignition timing with a crankshaft signal. Then we're going to have 2 different waveforms, but it's still going to give us 3 channels. Okay guys, this would just be the number 1 signal. This isn't the ignition event, so this is just seeing the computer is sending the signal at the right time. Now these are not going to line up perfect like how the camshaft did. These are lining up right in between the teeth. The actual firing event would be to the right of this on the crankshaft waveform. Or you could line it up below it. Same thing, whatever way you prefer. You could always use the cursor. It's always available, but if you have both channels in the scope, it's so easy to just drag one on top of the other and, you know, call it a day. Right in the middle on that side also. Alright guys, so this is the basic setup I got. I made a BNC cable going to a piezo sensor, going into that PVC, and I put it in this camera lens bag. And I got a piece of rubber hose off the end, and I'm just letting it dangle by a little bungee cord. And right in the middle is going to be your best vacuum port. If you could get a port that's central to all the cylinders, because the ones in the back are going to be pulling on it weaker than the ones in the front, but it's better to at least know, you know, side to side, you're not above one bank, you're in the middle. But I'm going to start it up, see what it gets, hopefully it works. Okay guys, I'm going to just start it in oscilloscope mode. I'm going to see if we get a signal out of it. That's cool, see something. Okay, we're going to go to automotive module. Keep it on 20 milliseconds. Got my amplitude down as low as the 512 goes, 1.1 volt scale. Under 50 kilosample. Record. Now I'm going to take it up to about 2 grand and hold it for a minute. Maybe do it a little bit higher, see what happens to the vacuum. Alright, beating on Pastor Ed's Honda. Let me stop that. That's awesome. You can see on the bottom when we accelerate, they're not really measuring voltage. See it overscaled right here. It's not really measuring voltage, but it still is getting a average of positive or negative. Whenever it's being pushed on, it generates a positive voltage. Whenever it's being pulled on, a negative voltage. So as we run up, it's generating the positive voltage, because as it accelerates, it's losing vacuum. It would have, I don't know where it would have tapped out, because these meetings are readings are meaningless. It's not measuring nothing, it's just which way it's getting hit. You could kind of tell which way it's leaning without measuring. Because you see on the D cell, where vacuum would have been the greatest, it's way down here. It actually, you know, underscaled. I overscaled the reading. But all right, that's pretty impressive for compared to what I thought I was going to get. We're going to whoop Pastor Ed's Honda one more time because I don't want to save a waveform that wasn't on the right scale. I don't think I'll need higher than 3.3. Then I'm going to do basically the same thing. Alright, stop that. It looks a little bit better there. Still overshot on the vacuum, but that's alright. I'll take that for a test run. But it's the same thing on a D cell. It's going negative and positive. But mainly what you're looking for is intake valves, even intake leaks. Anything like that is going to give you, it's kind of hard to do on a tripod, but if you count the pulls, you know, sometimes you even count it in between. You got to determine what repeats that many times. However many intake valves you got, each one's going to pull. So you got to figure out what's repeating. You could see some repeating patterns. You go from there. We're not going to get into that. We're just making sure this thing works. There's a lot that goes into analyzing that. And we don't have a sync right now. This is just basically testing it out. I'm pretty happy with it so far. Okay, this is a flight of the pulse sensor. You can see whenever we accelerate, we're getting a positive voltage. Whenever it decels, goes down, just like would expect. Seeing the individual pulls, when you zoom way in, these peaks are the pull. The negative is the intake valve sucking vacuum. Whenever they open up, we get a spike on the bottom. Whenever they let go, it bounces back and you get the little positive swing back. Now it's hard to line up the cylinder identifiers. You could either put a low pass filter directly on your waveform or turn on the math channel, which would be just a spitting image of your waveform because there's nothing to compare it to. Put the low pass filter on the math channel. The low pass isn't getting rid of anything except for noise, so we're just as easy to put it on the whole waveform. But if you want to look at both just to see what was noise and what wasn't, then you could put the cylinder identifiers on. The low pass makes it very easy. We'll go 1, 2, 3, 4, 5, 6. and then you just move the line until you're on the bottom, the downward pull, until you have your firing order on each downward pull. Just move it till the numbers match the downward pulls. They'll all space out. If you line one of them up, they'll all line up. If not, there's your problem. It's all right. Pretty cool so far. All right, one last test. I got the rod key out just to show you. This is the rod key. I forgot if it has a name or a number, but it's just a pulse sensor. I believe it's going to get a higher voltage, but we'll see. I've used it a lot of times before, but you'll see what I mean about the waveforms. It's the same kind of pattern, but I just want to compare how close they are to each other. Okay guys, this is letting the rod key rip. I've used this sensor a lot before, and it's, always given me good results in the intake or in the exhaust. In the intake, it is on the upper end of voltage. See, we overscaled up there on, I believe it's an 8.8 volt scale, but you could tell we're going to be well in the 16. By the time that thing stops, right, 14 somewhere in there, just guesstimating. It's a little bit more jagged, but it's, still, this is what I was used to, finding these tips. And one thing that was always a little bit difficult, the ones with the V, you can't tell if it's another pull or if something's going on. In the math channel, low pass filter doesn't seem to clean it up as much. We still see a little bit misleading peaks even on the math channel. This does have a much smaller diaphragm. I have a feeling that that's what affects how much voltage it's producing. So you could see where it was clipping there. If that would have kept going, we'd have been at least over 12 volts, and this isn't even the hardest snap. So definitely check the input voltage of your equipment before you do it. Like this is a 512, and I should have been on the upper limit, my highest scale. So even for the cylinder identifiers, it would be very doable, but I don't know, it looks like the homemade one got a little bit rounder, easier to line up, and for some reason the math channel never did seem to do much to this. Maybe I should try a different frequency, but it didn't round it as much as it did on the homemade one, put it that way. I'll put them side by side so we could take another look. Alright guys, before I was even done editing that video, I'm checking out my buddy John's car for inspection actually. And I seen pretty good access to a crank sensor on the Toyota RAV4, so I'm going to show you how quick you can get a cam and crank correlation with a very budget-friendly oscilloscope, and why I use that little Hscope. Alright guys, this is underneath the wheel well. The crank position sensor is right there. It's an easy to get to. That's on to show you how quick you could do this. But whenever I'm hooking up the signal, this little Hscope, it just lays anywhere you want. Once you know you're getting a signal, it's easy. I just unplug it and I leave the lead laying on the ground, get it out of the way, get the next signal, then get out Hscope. So you guys, it's just that easy. You put Hscope right on the intake, And then you back probe the signal wire for this would be the exhaust camshaft, and then we're going to do the intake camshaft. But right now we have two channels to start with. We're going to go for a cam crank correlation with the exhaust cam. Alright guys, started it up, wheeled the card over, got Hscope on. That way we knew we had two good leads from the Hscope. Now you plug it right in. This is still oscilloscope mode. This is what opens up first. We know we're getting a signal, so I'm going to move it on to automotive module. 20 milliseconds of both my scale set. 150 is perfect. See, we're getting a signal down there. We're going to just let it go. The car's warmed up. I'm going to just accelerate a little bit, then I'm going to stop it. I just like taking them up to about 2 grand, because that way you do find some slop sometimes. Okay, I got in it and I ran it up to 2 grand. This is what we're looking at here. Now I'm going to stop it. And this is a VR sensor. I mean, technically it's an AC wave, but you could look at them on DC. There's no real AC it's riding on top of. If you change it to AC, you're seeing the same signal. But now that's good for what I'm looking for. You could set this any way you want to look at it. That's what's nice. And this is a standard way you see a lot of these when you do find a node good. So this way I'm going to stop it, and we're going to just jump on to that sensor right there. Now it's a little bit hard to see, but right there with the red wire coming out of it, that would be the intake camshaft. So we're just jumping from there to there. Alright guys, jumped over to that one. This is oscilloscope mode still. Getting a signal, that's all. Turn it on there and I'll jump over. Once you got a signal on scope mode, jump over to the automotive module. Let it go. Okay, we're back to oscilloscope mode. That's just getting the crankshaft position sensor. Now it's just as easy as getting the Handtech, the signal probe for coil on plugs. It's your favorite, an HT25 on a stick. Oh guys, the paddle probe isn't getting a signal. When you hold it over, sometimes the coils are too well insulated. I can't even get the beginning of a signal with it on any coil. That's what makes the cart nice. It's easy to get right in, get an attenuator without even shutting the car off. We were going from trying to get secondary, and we're going to get primary. It's just a Handtech one. We're going to put that on the end of this lead. Give it a shot. Okay guys, now you can see we're on the signal. You're straight in. I did use an attenuator. It's not that high voltage. I'm on a 63 volt scale. But now we know we're getting the signal. Gonna go to automotive module. Hit record. Keep it at 150. Change this to 20 milliseconds. Let it go. Alright guys, one last signal, being something so easy to get. We're going to get the signal from the ECM to the coil of the fire, not the actual firing event. So this is the signal. Still on scope mode. Going to do the same thing. Go to automotive module. Now go past the automotive module and go back to it again. Hit start. Then we know where the signal is in relation to the crankshaft signal. That's all we needed out. I'm going to stop that and save that, finish checking his brakes, and I'll be back with this. That's what's nice about this. You could save all these signals, take a look at them later on. You got 4 signals in one warm-up cycle. Okay guys, I'm going to just show you how you line this up with a known good waveform. This is one that I got off of rotkey.com. They have a waveform library. It has a lot of good useful known good waveforms on. This one we could see we don't have an ignition sync, but we do have this would be the intake cam, this would be the exhaust cam. The bottom one is exhaust, this one's intake. But you could either look at the edges and try to compare them with the graph, but you need some kind of program that lets you draw a straight line to see which edge, whether you're going with the rising edge or the falling edge. You want to line this up with the teeth or the signal coming from the crankshaft sensor. So I used Affinity Designer. It does a pretty good job at it, and I'll show you what it looks like and then how we could count the teeth on Hscope, one cam at a time, comparing to the crankshaft signal. Alright, so I just drew a straight line going up from the intake. This would be the going right to the front. Let me see if I could zoom in any more on this. You could see we're splitting the bottom of this wave right in here. So we're going to look at our Hscope capture, and we're going to make sure this jives with it, because this engine has about 160,000 on it. That quick, we just want to see how good the timing chain is on it. Maybe somebody replaced this one before, you know, he just picked it up recently, but it's good to be able to compare timing this quick. Okay, you can see on Hscope we're looking at the same thing, but on Hscope I don't have to use another program to make the line. I could just drop the cursor and check the line like this, or I can move the whole waveform up until it actually touches. Oh, I don't think I took an image like that, but you just drag the waveform right on top of the other one. But right here we could see we're touching. That timing's dead on, at least with where our known good is. Okay, and here we're doing the same thing, only we're taking the rising edge of this exhaust camshaft. Right in here we're going straight up, and you could count the waves. 1, 2, 3, 4. It's splitting the fourth. Let me switch back over. Move a little bit closer. See, 1, 2, 3, 4. So now we're going to go back to Hscope, line that up again. Okay, next we go back to Hscope, and we could see 1, 2, 3, and with the cursor we're splitting the fourth one. 1, 2, 3, right in the middle. So that timing's pretty good. And a pretty quick test, and I mean you could see the results, even getting a known good from a scope that isn't the same one that we're using. Okay, one thing about ours is we included not only the ignition signal, but the actual ignition, the firing event. And then on just to move it up, and you got to be careful because these are very close. This is the signal to fire. Do you see how close this is on the second downward wave? On the second part, this is 360 degrees of the crankshaft rotation. We're looking at 720 to get all 4 firing events down here. So if you put the cylinder identifiers on it up here, 1, 3, 4, and 2, you could see this would be more or less the companion cylinder, the 2 outside cylinders. It's not a waste spark, but as far as the crankshaft goes, they're, you know, outside, and these 2 are inner cylinders. So to keep the balance, they both fire naturally. I believe that's why they fire where they do, almost identical, because they're both at the top, only 360 degrees apart on their strokes. So the signal comes earlier here and just a little bit behind here. So you don't want to be comparing this to the first 360 degrees, because you'd be looking at number 4's firing event and looking here, and it would be advanced. To the right is advanced and to the left is retarded on the waveform. So let me think about that. Yes, so the ignition signal would seem advanced if you expected it here and it was behind here. So you want to make sure you're looking at 720 and you have your cylinders identified. And see, what's kind of cool about having the ignition signal and being able to zoom in on it and move it around is you actually see what's going on. This is the signal. And if we count for number 1, this would be, we're going high, low, high, and then on the bottom of this low, the signal is straddling it. This is why the signal's important for the timing, but you want to actually see the ignition. This would be the computer signaling the coil to fire. This would be the actual firing event. The signal was over here. This is where it started, signaled the coil to fire, pulled it to ground, and it fired. And that's important because it's very close if you're lining them up. Where it got pulled down and where it fired, this would be number 4 firing. It's slightly behind the 3rd low. Number 1 is directly on the 3rd low. Number 4 is firing somewhere here. The computer has to have them separated. Being it's not a wave spark, it knows which cylinder by this waveform, which is number 4 and which is number 1, just by that little bit. So they're close. On the wave spark, it would be firing the same. Both of them would be close enough to top dead center. It would fire every time. This, the computer knows this is number 4 and this is number 1. So when you're checking that, like I was saying, the signal's important. I mean, it's good to know that the computer is pulling this down, but the actual firing event to check your ignition timing, you'd want this KV spike right here. That's the big bang. All right, guys, I inverted that back to where it belongs. Sometimes when you have the signal straight up, you could see it easier on the crankshaft, but going back to the 5 volts, I noticed playing that back that every time right after it fires, we do get a blip. This is right where this would still be on the primary side. I mean, these are injector noise, things like that. These little specks you see, it's just always right before the actual KV spike, that the blip of the cylinder firing. So I mean, you're actually getting to get the signal and you're actually seeing a little bit of a firing event. It's not much, but it's after every one. That's why, I just felt it was worth mentioning, because I see it after every one of these. So there's a signal, then this is a little bit brighter than all the other ones. But see how many of those are. There's injectors, other noise, but these smart coils, I mean, they're hard to back probe, they're hard to get a good primary, they're almost impossible to get a secondary, but you could see we could get the signal, but we're getting all four off of one coil. Okay guys, I figured I'd just put in a little bit of practical use of these cam crank correlations. This adventure, it started off like many on Rodkey.com looking for a known good cam crank correlation. Now the thing that was interesting about this car, the code was, I can't remember the number of the code, but it was for unexpected fuel pressure in the fuel rail. It was passing all the tests running on the Honda software. It was a 2013 Honda Accord with a 2.4. Now this is a GDI engine, and right here is your fuel pump. It's turned over by one of the lobes on the exhaust camshaft. That would be this purple trace. This comes from Rodkey. This guy, I've gotten a lot of his. I find myself the author of these that uploads them to the database. I've used quite a few from this author, and he leaves these cursors on here, so I didn't have to go back into Affinity and leave these lines here. He does some detailed waveforms, which are always great, because even though we're not using the same kind of scope, this is probably one of them MT Pros I believe he uses, but I know he does a lot on Picos too, but it's easy to, now that there's a cursor on there, we could see, zoom in real close and we'll see where that threshold crosses. This line goes straight up and it's barely on the downward slope after the big sync marks. Now we're going to go look on Hscope. Okay guys, now on Hscope it's going to be pretty obvious where our problem's coming from. The known good is over here somewhere. So if the edge of this camshaft, this is the exhaust camshaft, this is what's driving the fuel pump, it's a good bit to the right, which means advanced with the crankshaft. So this is hitting the fuel pump, and we're getting fuel pressure before the computer expects fuel pressure. That's what the code is. The car only had 60,000 miles on it, so you wouldn't think timing right away. But I mean, Honda, they had a few bad years with chains also, so you know, they're not indestructible. But here's where we were supposed to be, but this is still giving us time. In timing, we're going to want a degree. So I put the degree markers on 720 because this would be one full camshaft revolution, two full crankshaft revolutions. And you're going to have one cursor in the middle for adjustments to slide. But what I did next is just drop the cursor from the menu right where the timing's supposed to be. And then I moved from here and I put this degree marker right on top of where it's supposed to be. And then we have 6.8 degrees. It doesn't matter where you sync to, as long as you sync two crankshaft revolutions, a degree is going to be a degree. We're not timing the degree with anything, it's just in increments that we could count now, not just a time measurement. So if we're at 6.8 there, the next thing I'm going to do is line up where this is. And that's going to be 11.7. So if we subtract the 6.8 from it, we have 4.9 degrees. Now 5 degrees might not sound like a lot, but the 5 degrees is in crankshaft, degrees of crankshaft rotation, because we're on the 720 degree scale. So for camshaft rotation, you double that. So you're looking at almost 10 degrees on the camshaft timing. So That's what was happening. That camshaft was hitting the fuel pump before it was supposed to, due to slop in the chain, this slop. So sometimes on this was a GDI, there's some cars that could go with that amount of slop and not have any problem until there is a problem. But on some cars like a GDI, it's an incredible amount of fuel pressure. It was, I believe, 500-600 pounds at idle. If the computer detects it any earlier or any higher, it wants to put you in limp mode real fast, and that's what it was doing. The timing chain fixed a fuel rail problem. So on GDIs, that's just something that you could use. If you could get a known good that easy off of a different type of scope, use it on what you have in front of you. The camshaft, the exhaust camshaft is the one hitting the fuel pump, but we could have measured this on the intake cam too. It's going to have the same amount of slop in it. But it was just, this is the culprit. I mean, this is the player, so we wanted to see right where its signal was. So that's just a little bit of, real world experience to use a very quick signal and get as many known goods as you can. But even if you don't have any, there's a lot out there. Okay guys, I figured it'd also include like an explanation of how a pulse sensor actually works and what we're looking at. Whenever we fire it up, like down here, or before we fire it up, it's plugged in, it's ready to go. It's not generating any voltage, it's not moving at all. Whenever we started the car up, this is what you get at idle. We're at 0 volts. It's making an AC wave, which means we're going to get positive and negative. So down to here, it's minus 200. Up here, we're a little over 250. But if there was going to be any measurement, you would do it in between here. And like I said, a lot of times we're not measuring for these. We're looking for the different one. Like when we get to here, we're coming down off of this snap. The sensor isn't generating 2 volts each time by the mechanical pulse. Some of this is the top charge. It generates a surface charge the more it gets hit in the same direction. That's why whenever we're losing vacuum, it goes up. And whenever we're generating the most vacuum is whenever it goes down. But there's something that happens in here. These are the biggest pulses we're going to see on the whole waveform. And an easy way to find them is, you could use the math channel. Let me show you that. Just a simple frequency on channel 1 is going to get you, you're going to see a blip right here. And if we looked up, that's right where I showed you them biggest pulses. Now this is after the snap. The only thing that happens here is the throttle plate closes. When that throttle plate closes, it's going to be the biggest generation of vacuum, because all of a sudden we're breathing fine. And when we take the foot off the accelerator up here and the throttle plate closes right in here, we get this huge dip in vacuum. Right there's where the math channel, right in front of that. If we follow that up. I just expanded the math channel a little bit, and you could see the frequency change in here. You could see with your eye how solid this gets. As you could see, this is still, the math channel is still a higher frequency until this voltage gets back down to idle to 0. So it's responding to frequencies, responding to vacuum very good. The strongest pulls we're going to get out of the whole waveform are going to be right here. Even though we snapped it here, the engine's decelling, generating the most vacuum it's going to, and then whenever that throttle plate closes the whole way, the vacuum takes a nosedive. That's what we're expecting. This, guys, I just want to show you, this is with band pass filter. The last time I was looking through a low pass filter, this is a band pass. It's a high pass and a low pass. And I applied it to the math channel again. You could apply it to your actual channel, but this is just so you see both. Makes each pull much more identifiable by taking out the noise. Then you could put the cylinder identifiers on much easier. Line them up. You see, it's easier to do this on the red on the math channel than it is to do on the actual signal, because we're taking all the high and the low noise out of it, and we're just getting good pulses. Or you could line up your cylinders that way. What's cool about Hscope too, you could line them up, and then you could hit lock, and then they'll all move the equal amount. Or you could hit the infinity button, which is going to layer them on all your cylinders the whole way down your waveform. But the thing with this is your RPM changes. These are not going to be that accurate. You're better using it on a little piece of waveform. It's going to stay in time, for a couple screenfuls anyways. Then you're going to want to check make sure the cylinder identifiers are lined up again. We could see they're off a little bit. They're still pointing to the right cylinder. Helps you move around pretty quick, but see how much nicer the pulses look with a band pass on it. This is one thing that's pretty cool. With the high pass filter on, our math channel is going to stay linear. We're only going to see the pulses. We're not going to see that surface charge making it rise in a positive direction when we lose vacuum and descend whenever we generate vacuum. It's going to stay. Well, right now it's at minus 157. That's where the math channel, I just have it set. But it's measuring the pulses, and you see it's not climbing the voltage. So it's a little bit easier to just go straight across your screen without having to adjust to see the top of it. You could see in there we're staying straight across through a snap throttle. Just helps you line your pulses up a little bit better, because you want to be able to tell what is a pulse and what is noise. And that's where that math channel, low pass filter, band pass filter, they both help you greatly. Okay guys, that was just a quick tried to explain how they work. I hope it made sense how a pulse sensor works. They're different than a pressure sensor. Like a pressure transducer, we're actually measuring a set amount of pressure. To tell you the truth, the pulse sensors, they look much more exciting on a scope. Sometimes, you put a pressure sensor in the exhaust or something, it's just little humps. That's it's doing its job. It's measuring the back pressure, but it's not as excitable, and it always returns to zero. That's if it's a pulse like that. So you get nice smooth humps. It's definitely not as exciting, but it does what it does. That's what we'll do next, and I'll show you the difference in comparing them. And I'll show you how we're going to build a pressure transducer also to use for, vacuum, for exhaust, for coolant, for in-cylinder pressure tests. That's going to be a next project. That just down here, we're going to build sensors that we're going to use in the garage. Fix any kind of electronics, anything that we could put on table, we're going to put on table. If we could fix it, we're going to fix it. But I'm going to show you what's inside these pulse sensors. They're not very hard to make. The parts are cheap. Your enclosure, you could reuse something. You could use a plastic container. Joe's garage, it's almost identical to the one he built. There's different ways, different kind of leads. I believe he left banana jacks in it. I put a BNC cable on it, and I'll show you. I had two screws I was going to just use as like posts to put alligator clips on. You don't have to get that fancy, but if you stick around, I'll show you how we crimp BNC connectors, different kind of coax. There's a lot of different kind of coax out there if you're going to get into making your own leads. And It saves you a lot of money if you make your own. I mean, and you get some better shielded wire. I'm going to show you the shielding on this wire. It's not top of the line wire, but it's not bottom of the line like you get with Hantac leads. So you're getting up in the middle. You know, you're getting a lot more shielding for your money. But yeah, that's something for another one. I'm going to show you what's inside these and how you could easily build one yourself. All right, guys. All right, guys, here's the guts. This one I made, it has an 1/8 inch fitting in it. And I used the BNC on the back of it. I did have another one. I was going to make 2 identical sensors. But you could customize these either way you want. You could put, these are 1/4 inch, these are bigger. You could put these in another sensor. I'd like to have at least 2 with wires. And then you could just change the cap and put a 1/4 inch sensor on it. These are pretty tight caps, and if they did get loose, just a little bit of RTV around it, not enough to glue them together, enough just to make friction, and then they seal pretty good, especially going into something. Now this is just a photo lens case, an old 35 mil I imagine, and I just put a hole in the end to put the hose down. You got somewhere to hook it from. Wire hangs nice to the side. Inside of it, so see, you get 20 of these. It was well under $20, or well under $10 actually. These are 35 millimeter ones. These are larger diameter sensors. There's a whole nother pack under there. They're larger than the rod key, the sensor. That's why I think we're getting a little bit of voltage, because if it's a smaller version of this in there, it's going to react a lot. You know, just more mass on this. It's not going to vibrate quite as much. So these are very cheap, and there's enough for 20 sensors in there. And what I did on this end, where the sensor is, there's no glue or anything. These fit. That's why I went for the bigger diameter, the 35. It fits in there so tight. Just going into the threads where this screws. On the inside, I have the 1/8 inch again. You could again do this with 1/4 inch if you wanted. You could try it without this in there. Whenever it's together, that's blowing right onto that sensor. It's literally right in front of it. On the back end, this is RG316. This is very heavily shielded, a lot more than Hantac leads. So this is where we get a lot of that interference on the scopes. Whenever you make your own, you could get better wire, heavily more shielded wire to, you know, help with your signals. Now, I didn't epoxy this down yet because I just wanted to put a little bit of epoxy here to hold it. What I know I should have did, there's a little bit of plastic casting there, and it was easier to drill a hole beside it. I should have put the hole right in the middle, because if you're going to unscrew this, I hold the cable steady so the cable's not twisting the connection, and I'm just unscrewing the cap. But it makes it a little easier if that hole was in the middle. And those are the wires that came on the sensor. The center pin of the BNC is soldered to one, and the other one, the braid is so heavy, and I didn't want to solder onto a little braid. I used an inline connector, crimp a lot more of the braid than you'd be able to get that hot to solder to, if you know what I mean. You'd melt through the inner connector. So you got an inline crimp with 2 pieces of shrink wrap on each. Then just screw it back together, and it's, you know, it's a little bit customizable. You can turn it into whatever you want. You could put a real big end on it for exhaust. You know, you go up 1/2 inch, 3/8, something like that. You move a little bit more in there, air in there. Exhaust isn't very high pressure, but it's it's coming in a big diameter. So a bigger diameter here and a bigger diameter on the end would probably do a lot better in exhaust. But that's all I mean. You could just keep your settings the same, switch the cap, take a different peek, see if one's working better than the other. But I'm pretty happy with that one, especially since it ended up being by locking right in the middle of the HS 512's range. So that's where you want to keep your sensors. You don't want them on the upper limit or the lower limit all the time. Your target range should be somewhere in the middle of what you're going for. Because if you have a 5-volt input scope, you're going to have to attenuate for almost everything. So you want to use that for 5-volt and lower. You can attenuate some more higher, but the higher your input voltage, the less you're going to have to attenuate. And we've seen that rod key, it was way up there in voltage. So, all right, I'm going to show you the next project on that next sensor we're going to make after, we're going to be developing this one and making another one. Okay, guys, some of you have seen this before on my channel. This is the JH-APT-100. It's a pressure transducer kit. The only thing good in it is the actual transducer itself. This is a pretty cool unit. It does have rechargeable lithium ion in it, which makes it convenient. But the only thing you're really paying for is this transducer. This is a transducer out of a Honda. It's a fuel rail transducer. It goes up to 1,000 PSI. A genuine Honda one is $25 on eBay. Now that's an important part of what we need. This is a different kind. This one has the same 1/4-inch threads. And it also has a cord. And it was around $30. So let me give you a quick tour of what you get with when you buy this kit. This hose, which has horrible crimps, does not last long, and it has a non-universal quick connect. Might get you a couple times, but it's going to start leaking fast. You get this pipe. This is aluminum pipe. Use these to keep the piping as rigid. For in-cylinder pressure transducers, you want it as rigid and as short as possible. It's aluminum, it's going to leak. And it's not very heavy duty, and it's this long no matter what. Now, I upgraded the kit. These are pipes from Rotke. These are much more solid and shorter. So if you can use a shorter pipe, you can. So that's one thing I had to upgrade from this kit. The hose, I upgraded to a Rotke hose. They're actually brake lines, but look at the difference in the crimp on this and this. This isn't going to leak. It doesn't leak. It has a very thick brass and a very thick brass bottom. So it's a superior hose. So I had to upgrade the pipe and the hose already. So there's not much left other than this or this and the battery. So if you're going to upgrade, and if you're going to get into using one of these, you're going to want the better pipes and a better hose anyways. So if you buy those, you don't necessarily need to buy this, because everything, let me grab another piece and I'll show you how a lot of it goes together. Okay, now this is mainly how I keep this, and I use this with the quick connect high flow fittings. So you could just pop it on, pop it off. But now, the one thing that's important, the part of it anyway, is this is just a high flow air fitting. This piece here, this is from Napa. This is what takes you from 1/4 inch to the M12 for the spark plugs. This is for blowing air into the cylinder while you change the valve springs or the valve spring retainers on a car. You use blow air. You take the spark plug out, put this in, blow air into the cylinder, and then you could take off the valve retainers. Now it was, I believe, $6. Now that's a part you might either have to find online or, you know, go to Napa if you have one available. With this transducer being its 1/4 inch, you could go straight into the pipe, and you could have a very short transducer. You could use the fitting that goes straight in even shorter. You could use a pipe. Now, a union like this would have been better, but I have a T. So I'm just showing you, if you wanted to put like a blow-off valve for some of the compression, whatever you needed to do. This also. You'd have your transducer. You could put whatever you wanted on the end, another pipe. So you see you're saving on some of the pipes, and these are thicker and they're brass than what comes with the kit. You could go straight into the rod key hose. So you're saving a lot of money over a kit that this is all you're basically going to use. And you could use this or this. This has a smaller fitting. I believe it does anyways, because it's a fuel pressure sensor. Yes. So you play around with them to see which one you like, but if you do use one like this, you need the factory harness, the plug that goes in here, so you have all your leads. And on this one, it actually has a shielded lead. It's just the foil shielding, but it does have the lead. And then you have a ground, you have a power, you have a signal wire. So that's all we need is power, ground, and then we get our signal. Same thing as this, only we're going to have to use the Martin's custom probe calculator on the Hscope cloud to set this up. It has 175 psi max, so it'd be great for in-cylinder. And let me show you one of my ideas on how to power it. All right, this is something I actually got free for reviewing. So I put it together, and it's a 5 to 12 volt power supply. Now, a pulse sensor or a pressure transducer shouldn't take that many amps. This is a low amperage, but the sensor itself is from 5 to 12 volt range. I have plenty of battery packs. I have plenty of other ways to power the sensor, even another variable, but maybe 7 or 8 volts is its sweet spot. I don't know. Maybe it's going to respond the same to 5 volts as it does to 12. I don't know yet, but it's nice to have this variable to crank it up, 10 volts, 12 volts, see how it responds. But I'm going to take these leads off, and just put banana jacks on to make it easily connectable. And it's kind of a drag to have it plugged in when I do have batteries, but it's just kind of one of them things. If you make your whole sensor the whole way, you may as well assemble the power supply too. Plus, it's pretty good soldering practice. But that's the idea for the next one, to build our own from the power supply to the actual pressure transducer and sensor, get it running and see what kind of results we get compared to this. Sometimes you build a sensor like this is going to save you money over buying a kit, because you still want to upgrade the kit once you get it. The pulse sensor, they're pretty cheap from Rodkey, and I've used that Rodkey a lot. It's a very good sensor. You could time the cylinder to the exhaust pulse, the intake pulse. It's a very good sensor, but in the end, it seems like the one that I made, I like the results, but that's just one test. The next one, the Rocky might outperform it. Sometimes cars, you know, it's a little bit different, but that was a 250,000 mile Honda. That's not a very good engine to get intake pulses off of. And we still did all right with the homemade one. The Rocky did all right too. We could have timed them to a cylinder, but in the end, I'm pretty happy with that, guys. But all right, thanks for watching. I'll let you go. I'm sorry it's so long, but I just kept adding more things as I went. Hope you enjoyed it, and stick around. We're going to be building a lot of things down here and using them up there. All right, guys. Adios.